Hi, my name is Colt Correa, and I'm the COO of Intrepid Control Systems. And what we have here is a couple products that support relatively new 10BASE-T1S automotive Ethernet network. And 10BASE-T1S is a relatively new Ethernet type network that is built on a bus or multi-drop topology, and it's specifically designed to compete in cost and functionality with legacy networks such as CAN-FD and FlexRay. So this is automotive Ethernet's entry into a bus or multi-drop topology type of network, which has big advantages over cost savings and cable savings, weight, and so forth. So the two products that we have on display here are the Rad Meteor and the Rad Comet. The Rad Meteor is a small, low-cost device in a plastic enclosure that has a screen and some buttons, and essentially we have one 10BASE-T1S network here coming in, and then USB up to a host computer. And then the USB on the host computer enumerates itself as a Ethernet NIC for the Rad Meteor. And each button on the Rad Meteor can put the PHY, the physical layer, the chip, into different test modes for 10BASE-T1S. Like, for example, this one is a test for time jitter. We have one for high impedance mode. We have one for droop test, and so forth. And you can download scripts into the device to transmit data. And the other product that we have, this is more of a professional network product, is the Rad Comet. And the Rad Comet, we have two CAN-FD networks. We have a 100BASE-T1 network, and then also a 10BASE-T1S network. So here it's the same. 10BASE-T1S comes in on this connector, and then we have either USB or Ethernet, standard Ethernet, 100BASE-TX coming out to a host computer, and the USB also enumerates as a Ethernet NIC. And what we have here is our vehicle spy connected to the Comet that's measuring the automotive data, the automotive Ethernet traffic that the Meteor is transmitting to the Comet. The Comet's receiving the data and then displaying the data in our vehicle spy software. In the vehicle spy software here, we can see some status registers of the PHYs themselves. For example, is 10BASE-T1S PLCA active, which it is in this case, and then some other statuses like is there a collision detect and so forth. So with these tools, these are the start of full family of tools for 10BASE-T1S. It's looking like 10BASE-T1S is going to be a dominant network in the near future. Many OEMs are picking it up, and it's something that everyone should know something about. And the two products again are the Rad Meteor, Rad Comet, and my name is Colt Correa, COO of Intrepid Control Systems, and I thank you for your time.
Hi, my name is John Simon. I'm a Product and Applications Manager at Intrepid Control Systems, and I'm here today to talk to you about a product we have called Radmoon 3. Radmoon 3 is something called a media converter for Ethernet. And if you're not familiar with what a media converter is, Ethernet can be transmitted on a number of different media. You've probably heard of fiber. There's also twisted pairs, copper. The most common form of media is twisted pairs. Gigabit is typically 4 twisted pairs. But for automotive, there was some requirements that specific media didn't support. It was too costly because of the extra twisted pairs, and there were other concerns with electromagnetic rate emissions. So they came up with a single twisted pair called 100BASE-T1. That was back in 2012, 2014. Since then, it's evolved into faster and faster speeds, 100 megabit, 1 gigabit, and now multi-gigabit, and that's where the Radmoon 3 comes in. It's a multi-gigabit media converter between commercial or consumer Ethernet, which is 4 twisted pair, and automotive Ethernet, which is a single twisted pair. And the motivation for all these additional speeds is vehicles are evolving to a new architecture where there's a central compute module that's basically aggregating all of the data from all the corners of the vehicle. And so a very high bandwidth lane is necessary to bring all of that into that central compute module without a bottleneck. When the automotive requirements were identified, it was determined that an amendment was needed to an IEEE document that defines the physical media. And this amendment was known as 802.3CH. And this defined multi-gigabit automotive Ethernet, known collectively as multi-G base T1. And that covers 2.5 gigabit, 5 gigabit, and 10 gigabit all over a single twisted pair. This is full duplex operation, which means you have full bandwidth in both directions, as well as it is on a maximum of 15 meters with 4 interconnects. And this is quite different than the consumer Ethernet, which has a range of up to 100 meters. These trade-offs were necessary to meet the needs of EMC requirements, power consumption, and other things that are important in the vehicle that aren't important in data centers and in your home. This also supports auto negotiation, which means the different PHYs can negotiate speeds and different roles in this link between them, and also some energy efficient operation for low power modes when it's running idle or not at full bandwidth. Radmoon 3 is a multi-gigabit, multi-G base T1 media converter, which means you have 4 wire or 4 twisted pairs coming in, the consumer Ethernet, going through and being converted to a signal on a single twisted pair shielded for automotive Ethernet. On the front of the device, we have a user interface that will tell you the speed it's operating, the link status, whether it's sourcing the system clock or receiving it from its link partner, as well as if there's a valid link between devices and the activity being transmitted between the two devices. There's no buffering inside of this device. It also has an interface for setting the link mode of the device, and that has to do with whether the device is supplying a clock signal or using the other link partner's clock signal. It also has link activity and activity lights, so telling you if you have a valid link between another device, and then activity shows if there is information being transmitted between the two devices. On the side of the Radmoon 3, we have an indication of the signal quality index, or SQI, and this is directly proportional to the number of dropped frames due to noise or corruption on the link. And so you can see it has 4 green LEDs right here. That's the maximum SQI, and it goes all the way down to a 1 red, which is unacceptable SQI, and that would correlate with dropped frames and problems communicating between the two link partners. Another feature of this device is that it supports all of the test modes that are in the specification 802.3CH. And those test modes are for putting the PHY in a mode where, for testing jitter, for testing linearity, for testing EMC and a bit error ratio, and different types of insertion loss. So those are all in the specification, but you may have some needs outside of the specification where you need access to internal PHY registers. We have an open source API, and that lets your application, either Linux or Windows application, talk directly to the PHYs in this device. And this is very useful for advanced features like TDR, time domain reflectology, and that is basically a diagnostic mode where the PHY can detect if the twisted pair is open or shorted, and it can even determine how far away that fault is from the PHY. Another feature of the API is TC10. Now, TC10 is a technical committee of the Open Alliance responsible for sleep and wake up of automotive systems. And this feature is a very low feature built into the PHY, which means to use it, you need to talk to the PHY directly through registers. So you read registers to determine if a wake-up command or wake-up request has been received, and you write to registers to send wake-up requests to other devices and request they go into low power mode. So this pretty much sums up all of the features of the Radmoon 3. You can see it's in a very convenient small form factor. It's powered between 6 volts and 40 volts. Thanks a lot for learning about our product, Radmoon 3, the multi-gigabit Ethernet media converter for automotive Ethernet.
Hi there, my name is Samir Bhagwat, and I'm with Intrepid Control Systems. I'm Director of Quality Assurance and Engineering Services. I'm here going to talk about service-oriented architectures, and specifically about some IP. With the new technologies for the ADAS and autonomy, we do see need of high data transmits and a complex data type communications. With traditional signal-based communications, there are certain limitations, and some IP and service-oriented architectures try to address those needs. Intrepid has been part of providing products and solutions for some IP, and essentially, Vehicle Spy X and NeoVI are the products which have our own some IP service discovery stack. This means when you are going to test your architectures for some IP, these products could be helpful for you. So this is NeoVI Pi, which has a Raspberry Pi along with our CAN interface hardware. And this is one of the devices I would highly recommend to use for profiling and running your some IP stacks. It has Linux because there is Raspbian in there. And this device, along with a media converter and a switch, can form a good platform to architect your some IP running inside an ECU. Along with this, I would recommend using Vehicle Spy X. Vehicle Spy X has our own service discovery stack, and it is also accessible through Python interface. As you know, Vehicle Spy X is our cross-platform new modern architecture bus analyzer, and it has our own AUTOSAR COM stack for communication network testing. Conceptually, a service-oriented architecture is different than signal-oriented architecture because here there is a process where you can discover what services are offered by which endpoints, and that is called service discovery. Once service discovery happens, a provider and a consumer establish a contract, a runtime dynamic contract where provider is going to provide needed services to a consumer ECU. These all architectural changes are driven because of things like zonal architectures and software-defined vehicles. So service-oriented communication is the future, we believe, and with the new zonal architecture and software-defined vehicle architectures allows, with the help of the OTA, post-production update of the vehicles, which is absolutely possible today because of technologies like service-oriented architectures and some IP. Some IP is something not very new, and BMW, in fact, introduced that in 2011 as a middleware to do transactions when they wanted to have things which are independent of underlying hardware layers. More traction of this technology has happened in recent years when actually AUTOSAR specified it very clearly, and in the specifications in November release, the recent November release, they have a major change and upgrade to some IP specifications, including in-service discovery. And AUTOSAR remains on the forefront of the for specifications on some IP, and that is the technology currently every OEM is following for service-oriented architecture. And the main part is the description of the entire some IP architecture and how the data is transacted is very well defined in AUTOSAR ARXML. Intrepid supports ARXML technology, and Intrepid supports some IP through different product lines. One of the talk I have today is about how to use our media converters and switch to have different endpoints talk to each other on service-oriented architecture. Thanks for watching. This is Samir Bhagwat from Intrepid Control Systems.
Hi, so my name's Carl Hills. I work for Intrepid Control Systems Europe. In Europe, our Wi-Fi customers, 70% of our customers are actually using wireless data loggers. And one of the exciting new products that we want to bring to the market to support those is analytics. So the real reason or the motivation behind analytics is 33% of engineers spend their time doing data reports. It's all about grabbing the key performance indicators for management, metrics understanding to really quantify what's going on with their products, with the engineering facilities, and bringing a product to market. Analytics is the ability where we can actually grab the data that's already gone to our Wi-Fi servers, And then in an efficient manner, we can pass that data through to an analytics stack where we're able then to actually bring live metrics or near real-time live metrics to the customers, to the engineers directly, so that they can actually produce those KPI reports and really find those needle in the haystacks scenarios. So one of the things that we've learned as working with our customers for Wi-Fi is we upload a huge amount of data. So, a lot of our customers are uploading, terabytes of data per day, and a lot of that's for root cause analysis. You never quite know what's going to happen. So for some of our customers, they're doing durability, they upload vast amounts of data so that they can actually run through the metrics within that to understand certain scenarios that have been collected for root cause analysis. And we've got an array of tools which enable us to be able to support that and do that. But the missing part for our customers then was, well, all that data has been collected, but what about DDC metric trending? What about how long the vehicles have been running for? The efficiency behind understanding, what we don't actually know. And, engineers are spending 23% of their time looking for recreating conditions that haven't actually reproduced. So analytics for us is a way where we will produce bespoke dashboards, custom dashboards for our customers to really enable them to have their IP realized and enable them to produce that on a real-time basis. But also we've got basic default dashboards. That will give, those dashboards are the metric data that almost all our customers use on a regular basis. If you're using our wireless data loggers, you're going to want to know where the vehicles are at any moment in time. You're going to want to know what software they're running on. You're going to want to understand any DDCs that have been that have appeared. You want to know what software versions they appeared on, and you want to know where they've appeared. So we've produced standardized dashboards that will enable you to get maximum efficiency out of all of the data that you've uploaded. You have that ready to report, and then from that you actually will start to identify and spot any trends, any conditions or issues that need further investigation. And that's just one element adding to the ecosystem that already exists for us. And here we've got a complete solution for you. So one of this situation that we got here in this demo offers the low cost entry point data logging solution. And then from here, we'll actually be able to upload to the server, Wi-Fi server, which will push through to analytics, will enable you to see those core metric data. You'll be able to understand where your vehicle fleet is. And here you can actually see this in the map here at the top. And what you'll be able to do is have default dashboards. Intrepid will produce default dashboards for you, which will enable you to have fleet management, IUMPR, DDC tracking, but also logger health. Understand, are the devices that you spend time and effort implementing into your test facilities or test vehicles, are they working correctly? Are they uploading the data that you need? Are you getting the added value, which are the metrics that you can actually generate your reports and provide those to the management team within the OEM? From that as well, we can make custom reports. So if you've got IP data, if you're normally downloading data sets and post-processing those, we can work with you, generate a custom dashboard where that IP data will then automatically be generated once the data's been uploaded. And we've got examples from OEMs that have asked for this, like we've had customers that have asked for CO consumption or CO monitoring. So from that, you're actually, we could feed that in, generate the report for you. And that's something that you can't just grab data automatically from the vehicle. It doesn't exist. It requires computation, it requires mathematics to generate that. That can be built in and be almost in real-time availability for you. Nice thing that you can see here through the report is once the data has been uploaded, that will then be pushed through to analytics stack. And from the analytics stack, we've got key metric data. So from the key metric data, you can see that we can visualize that in a number ways. We've got that through actual raw signal data itself. We can plot some of that data. You can have GPS data assigned to it. And this data is actually enables you to zoom in and zoom out and gives you one quality sample of data. So if you've got an OEM with multiple departments, multiple vehicle platforms, you'll be able to actually dig down into those individual conditions to monitor those from fleet management right the way through to your IP related data and trend monitoring, or you'll be able to zoom out of that and actually be able to look at that across the entire range really giving you the ability to see, are we seeing these improvements? Are we actually having the trends monitoring? And are we actually confirming? So I think one thing coming from a quality background myself is Intrepid has now a complete ecosystem. Not only can you log the data, upload that data, you can then plot and trend the data and find out those needles in a haystack. Once you actually identify an issue of concern, you can then come back to that raw data, do root cause analysis. We offer over-the-air reflashing. And then the final part of that, which is so important from a quality point of view, is you can further post-monitor that situation to make sure that the problem has actually gone away and you don't have a reoccurrence. And if you do, you can capture it and identify it quickly. This adds real value to the OEMs, real value to the engineering departments, and brings a higher efficiency to those that are working within those departments and not spending quite so much time in generating the reports, downloading, uploading data, and searching, through all that huge, vast amounts of data points to find things that they were otherwise unsure of or was unknown. Thank you very much.
My name is John Mitchell. I'm a product manager with Intrepid Control Systems, and I'm going to be giving a quick review of our cloud-based data logging and analysis system that we call Wireless NeoVi. And in this demo, we have a simulator on the left there with the translucent enclosure. It has 4 pots on there that can simulate sensor inputs. You can turn the pots and they will vary just the voltage of the pots, and it will send the data from the pots over CAN on this diagnostic connector, which is being logged by our NeoVi Fire 3. The Fire 3 has 16 dual wire CAN networks and 8 LIN networks on it, and it can also be configured for FlexRay as well. And the Fire 3 can log data to its onboard SD card. It actually has 2 SD cards that you could run 2 terabyte cards, one in each of the slots to maximize data logging. And the Fire 3 logs data to the SD cards while it doesn't have access to the cloud. And then when it has access to Wi-Fi or cellular, it can upload that data to our cloud-based server, which is just a browser. And we also have in this demo our RadIO2 TC series that allows you to read 8 thermocouples per device, and then it sends that data over CAN to the Fire 3. And you can daisy chain different RadIO2 devices. We have some that will read analog inputs, some that will read thermocouples, and we also have others that can control relays and read digital signals as well. And I'm analyzing this data, and this is just a browser here. So you don't need to install anything on your PC in order to see this data. So you could be at home in your living room and just log into the website, and you can start looking at data without installing anything. And one of the benefits of that, there are time cursors in here where if you hold down like the number 1 and you click on the plot, it'll move cursor 1 to to wherever you click. And if you see something of interest, like this change mind shift here, you can copy a link to this view to your clipboard, and then you can IM that link to a colleague, and your colleague clicks on the link and it takes them to the very same view of the very same data. So this is not a screenshot of the event. This is the same data that you were looking at, that your colleague in another country could be looking at. So then they could look and say, well, I think I know what's going on there, John. I think it's a problem with with these parameters, and then they can plot some signals, on the plot as well, and then share a link back with you. So you can analyze the data together without having to move large data files, around, in many different locations. So it's really like a lot of other. It's really the one thing that sets this tool apart from all the other data analysis tools that I've seen. I've been working in powertrain controls for 20 years, and I've never seen a tool that has the ability like this to leave all the data on the cloud. And most tools they have you bring the data to the analysis tool. Like you record it and somebody gives you the data, you run a MATLAB script on it, and you've got the results. With our setup, all the data goes into one spot, and we bring the analysis to the data. It's all on the server, and you can access it from any client. And it's really makes collaborating with your colleagues, even internationally, very efficient and effective. Thanks for watching. I'm John Mitchell from Intrepid Control Systems.
Hi, I'm Don Hatfield, and I am the product manager for wireless BMS products at Intrepid Control Systems. What we have here is the ADI version of a chipset for communicating with wireless battery pack nodes. In essence, what we're showing here is pretty much what every customer initially wants and usually uses in their systems, in their test systems, in DV testing, PV testing, end-of-line tests, etc. Essentially, what everyone would like would be to get the data from the battery pack from each of the nodes, and then to take that data in from a manager, but then spit it out on CAN into other test systems, test benches, etc. What we have here is the battery simulator. So you'll actually see a row of small connectors that are essentially the battery simulation themselves. And I have a way to adjust that with a potentiometer. And also the node simulator. Both of these are actually from Analog Devices in this particular case. But this could be your own node and your own circuit board. So on the RAD WBMS, we have two antennas. These antennas are used to connect up to the node, or you have this iGrid connector, which is used for wired connections to WBMS Manager or to other associated ECUs. For the RAD WBMS Manager, we have two different options to connect to the device, to put it to your test system or to a PC. The first way is USB. So we have a USB connector here. You can also connect to it with Ethernet. So power options, there's actually two different power options as well. With USB, it runs without any additional power from any other connector. If you use Ethernet, there is no PoE, but we do have a micro DB9 connector that has the ability to use to provide power to the WBMS. And then finally, CAN also comes out that same connector, and we provide an adapter that gets it to a standard DB9. And then the WBMS is taking that data and transferring it to CAN, which is actually being read over the value CAN. So essentially, in a battery pack, you start out with a cell. Those cells are assembled into small, it almost looks like a very small battery pack, but I would call it a node. And then those several nodes are placed inside of a battery pack, and then it's sealed up and put into the vehicle. If you're using a wired BMS, this means you have to wire up each and every one of those nodes. So that uses copper, which is time in manufacturing, its weight and range and cost, because you're using more copper than you probably need to. And so in an ideal world, what would you like to do? You would love to have a wireless connection between each of the nodes so that there is no copper and there is no hand assembly or having to do any kind of wiring in between each of the nodes and the manager. A device that essentially is the brains of that node, and that's connected to the batteries, which in this case, we have a battery simulator, and then we have a node simulator, okay? And these are actually development boards that come from ADI in this particular case. You can have many of these, 12 or 16 of those inside of a single battery pack, and you can operate multiple managers at the same time with a single silicon chip. And what you see on the screen is actually what we call Vehicle Spy. Intrepid's Vehicle Spy software is essentially a tool where you can make your own graphical interfaces, put in code, and create your own tests if you'd like, as well as see the actual data coming out. So the data comes out of the battery packs, or out of the nodes, if you will, and then that gets transmitted wirelessly to the WBMS. Now, normally in a manufactured vehicle, each of these is inside of a single sealed case, okay? So all the wireless takes place within the case itself. But when you are in a bench situation and you need to talk to a node or to create a test, then you would have to have your own wireless manager that you can use. And so there's several different choices. One would be you essentially use the ECU that you're developing at the same time you're using it to be essentially a testing device to gather your data. Another way would be to get the analog devices boards. You could get the development boards to do the manager as well. But the problem with those is that, number one, your ECU is under development, so every time the code changes, you've got to change your test setup. And those ECUs are very difficult to get often at the beginning. With the development boards, those are not made to be produced in large volume. They're only for evaluations. So the option that ADI and Intrepid have worked together to make is the RAD-W BMS, which has its own APIs. It can be used as its own test tool to connect up to a node or to a set of nodes, just like the manager that's actually in the battery pack. As another option, on one end here, right between the antennas, there's actually a connector. That connector is made to connect via ISO-SPI to the manager itself or to other devices that are on ISO-SPI connected to the battery manager. So that way I can actually use the actual battery management ECU, and I can connect up the actual nodes, but use the WBMS as a test tool to load in new configurations, as well as to do testing of the complete system using ISO-SPI and the other associated ECUs. So in this case, I said at the beginning, well, this is actually demonstrating the most common use case. And I talked a little bit about CAN, and I haven't said anything about CAN yet. So the WBMS has a special feature which you can enable that essentially automatically creates a CAN gateway. So in essence, when you load the nodes and manager, depending on your test situation, when you load them with the configuration from ADI software, it automatically will create a gateway to CAN, and it will give you a database file that you can use to then use in your test tools and create the rest of your test. And instead of writing your own script or even using the gateway builder, which is handy for making your own specialized gateway, this is nothing more than a single click in configuration and then getting the database file out of our software. Then you can use it in other test tools. And to top it all off, this runs independently in that case. I could have this set up to do nothing more than a gateway. It's not hooked up to a computer if I don't want it to be, but I can hook it up to a computer, and I can also do the gateway at the same time, which is very common for Intrepid products. We try to do everything you need into a single box versus having multiple boxes for multiple systems like simulation versus reading the bus. For this demo, we're actually showing a gateway from WBMS to CAN. And so what we're showing here is the battery pack simulators. You can have multiple ones. We just have one in this particular demo, just to save for room. And then that's connecting wirelessly to the WBMS. And then you'll see that from the WBMS, it's connected up to the computer. In this case, we're using USB. The CAN is actually coming out not just on USB. In this particular case, it's actually coming out the value CAN 4 as a separate gateway. But this general graphic actually is not quite the same. You can do it this way where it's only going to the laptop. So as I change the potentiometer, you'll see that the numbers go up and down. And that's actually wirelessly being sent from the node to the WBMS, and we're picking it up through the wireless antennas. For more information, feel free to contact me. My name is Don Hatfield. I'm the wireless BMS manager for Intrepid.
Hello, my name is Chris Sabosian. I am the Senior Director of Business Development here at Intrepid Control Systems. And today I'm going to talk to you about our wirelessneovi.com cloud platform tool. What this platform tool allows you to do is take our newest hardware, such as our Neovi Fire 3, Neovi Red 2 devices, install them into your fleet vehicles, and via an internet connection, whether over Wi-Fi or cellular, enables you to control the data logger and upload data sets remotely. So we have today our Neovi 3 Fire hardware, which is our newest connected data logger. We also have our Neovi Red 2 line. And what those devices are enabling you to do is install them into vehicles in upwards up to 16 CAN-FD networks. Starting with our RAD-IO 2 line, what this does is we have separate modules. The ones you see here are thermocouple modules. Those are able to connect via USB to our data loggers. The data logger we have here is Neovi Fire 3, which is our newest data logger, which can log up to 16 CAN-FD networks, 2 terabytes of onboard storage, and full wireless capability and GPS capability. We have cellular capability added with our RAD 4G modem. What the RAD 4G modem does is also connects via USB to the data logger itself, and then can connect to cellular networks and provide you with 4G data connection. This device is a global modem, so this modem will work throughout the world. It will be fully certified in those countries and with various providers around the globe. And then the last item here is our Neovi Mic 2. What this device is a device that lets you push the button, activates a microphone and a trigger point in the data set, and uploads that to the platform, and giving you a time synchronized data set file and audio file for you to listen to, so you know which issue you're looking to in that data set. Furthermore, you can also sign up for data alerts. So let's say you wanted to be notified every time a certain vehicle had an event or something like a trigger button push. You sign up for those alerts, that button push happens, you're immediately sent an email with a link to that data set, and then utilizing our cloud-based tools such as DataSpy, you'd be able to look and view all of those signals, plot them, identify issues, and then share that data with the teams responsible for looking into that issue and diagnosing it further.
I'm Chris Sabosian with Intrepid, and thank you for watching.